Hello everyone, my name is Bhavya and I'm an electronics major from University of Delhi. I'm starting this YouTube channel to document my projects based on analog and digital circuits. And I'm going to be starting my first series starting from this video where I will be covering the STM32 microcontroller. This, this first video will cover how to make a blink circuit using the STM32 microcontroller, and then we will progress to more advanced concepts. In the next video, we will be covering PWM, which is pulse width modulation, but that's for the next video. So I'm going to begin with the blink circuit. Now, to the good part of this video, I'll be writing the code to blink the LED. I'll be setting up the software and I'll show you how it works. Let's get on with it. Here I have launched, let me show it to you again. Here I have launched my STM32 Cube IDE. Once you have logged in, you should see something like this. It will ask you to do some setup. You should follow along, it's pretty easy to do. Once you have done that, it will ask you to join a workspace. I have currently two workspaces. This is my default workspace and this is my workspace for my YouTube. So let's go into that and launch. It's starting up. I'll speed up this process on YouTube. Now it should show you something like this. And if it doesn't, you don't need to worry. You just need to find something called create a new STM32 project, which I'll be doing. It should initialize a target selector. We'll wait for that to happen. For this code, uh, while that happens, we'll talk about the code for a while. Uh, for this project, it's really simple. You just need to enter your part number here. So I'm using a STM32 F401 CCU6 microcontroller dev board. So let me just type it. STM32 F401 CCU6, and the first one seems like my part. Next. So I will name this project Blink. Finish. The other settings should just be left default for now. It's taking some time today because of the OBS. After that's done, we should see something like this. Here, I will be configuring my pin PC13 as a GPIO output. So before I do that, let me just explain to you what all of this means. It's a little overwhelming at the beginning. So this is the clock configuration. We don't need to worry about that for now. This is the pin out and configuration. So our main chip looks something like this, and all of these pins have been mapped here. And instead of initializing a pin to do something in the code, we can just do it from here graphically, which is a good thing, which makes our life really simple when we have to debug and when we have to start our projects. So I'll make the PC13 pin. I'll click on the PC13 pin. So I see a plethora of options here. I could use it as a GPIO input, GPIO output, GPIO analog, event out, and GPIO exit 13. You don't need to know all of what that means. We're just gonna be focusing on GPIO output for now. Output for now. So let's just make that GPIO output. And yeah, that should be about it. Now we Control S, save, and that should prompt us to generate code. Do we want to generate code? Yes, we want to generate code. So we click yes, and we open the perspective. It's gonna generate our code for us. It's gonna initialize that GPIO pin that we selected, which was called PC13. That's very relevant. PC13 pin to be our GPIO output, and we don't have to do anything for that in the code. So we are gonna scroll. We are just gonna see the structure of this main file. I'm gonna just minimize everything so that it's better visible for you all. Yeah. So this is our main code. This is where the user code should be going. We can this is include private includes, and all of this code has been generated by the computer by the ST's STM cube IDE. So this is the main function which is to be executed, and this is the super loop. As you can see, this is a while one loop, which means this loop will be executed forever. Once we've reached this point, we will enter the while loop and we will continue to execute whatever happens in the while loop forever. So let's say I want to I want to turn on the LED. So what I can do is I can use the HAL libraries. HAL libraries, HAL is a piece of code that ST has written already for us. Let's say we want to use the GPIO pins for output, and so you don't have, so if you were to directly use the GPIO pin, you would have to do a lot of tinkering on the uh, register level, which is quite hard to do for each and everything. So the HAL libraries already implement these functions for you. So we're going to use these HAL libraries, which makes our life really easy. So I'm going to turn the GPIO pin on using the HAL library. HAL underscore GPIO. And you can use the autocomplete using control plus space shortcut, which saves you tons of time. GPIO write pin. And so now the part where we use the where I mentioned the GPIOC PC13, that name is really important here. Why? Let me show you. So to write to the particular pin, we need to tell the function which pin we are referring to. So the first argument this function takes is the port. What is the port of the pin? The second argument this function takes is the number of the pin, which the number of the pin, and the third argument is the state, either high or low. So the port of the pin is C, GPIO C, and the pin number was 13. So we are going to use GPIO pin 13, and the pin state is going to be set, and we're going to add a small delay here. The function is called HAL underscore delay. I'm going to add a 100 millisecond delay here on HAL, and to turn off the LED, I'm just going to do HAL underscore GPIO write pin GPIC GPIC pin 13, sorry about that, pin 13, and the pin state is going to be reset. That should be it. I'm going to add another second of delay here. Of 100 milliseconds. Oh, or 1 second for that. So now with that our code is done, and now it's time to upload our code. To upload our code, we're just going to need and with that the code is done. We don't need to make any more changes to this code. We can just save this code, and now the schematic side of things is remaining. Let me show it to you. Here is the shot of a microcontroller. It is connected to this ST-Link V2 programmer that you can get online. Here's the top shot of the microcontroller, and this is a LED called C13. It is called the LED C13 because it is connected to the pin C13. This pin is also available as an output for us. So we can connect an individual LED as well as the onboard LED. Both are connected to this pin C13. So let me just connect this external LED to this pin C13. This probably should show us a cool effect that we'll talk about later. I'm just connecting a resistor to the ground because I don't want to short my LEDs. Where's the ground? There's the ground. And these are the connections. These connections, these wires, these have been connected for the programming of this development board so that we can upload the code via the USART interface. So I'm just going to plug this in. Now I've plugged it in. Now we're going to flash this code. First we're going to build this to check for errors. Let's build it. There should be no errors. Let's see. Yeah, there are no errors and no warnings. Next. When we click on this button to run flash, it shows this menu. I saw some video where someone told me to uh, enable ST-Link debug pro as open OCD if you are using a cheap ST-Link, but my ST-Link works fine with the GDB server, so I'm just gonna keep that. And you can leave all of this default. Just go to here and click OK. Now the code should begin to flash. Here you can see it starting to connect with the debugger. It's waiting for the connection. The download is verified successfully. And what was that? The LEDs are blinking alternatively. I have an answer for why that is happening. Because the LED C13 is pulled up and the LED C14 and this LED, the external LED we installed, is pulled low. So this LED, for this LED, the onboard LED, the ground fluctuates while this LED, for this LED, the VCC fluctuates. So if we connect the resistor to 3.3 volts instead of ground, we should see a similar result. We should see that both of the LEDs start blinking at the same time. Sorry, my 3.3 volt connection is just getting my hands in here with the camera. It's not blinking at all. And if we just switch the polarities of the LED, it should blink. And now, so what we did here is we switched the polarities of the LED and we connected the resistor to the 3.3 volts. And now both of these LEDs are blinking in sync. They are blinking together at the same time. And if I just invert this LED, connect the anode to the C13 pin and the cathode and this resistor to the ground, then they started blinking alternatively. It's not blinking, maybe the pin is wrong. Sorry about that. Yeah, as you can see, they blink alternatively. Now we know what is the difference between LEDs pulled up and pulled down. So now let us remove this external LED and I'll show you the output waveform of this PC13 pin while I connect it to a oscilloscope in rolling mode. Let's see that. I'll try to show it to you with steady hands. I've connected this ground to the ground of my probe. This is a ground on the STM32. I don't know if you can see it or not. It should be visible. And that red wire is connected to my C13 pin. This C13 pin is connected to the testing end of my probe, and now I will boot into my oscilloscope. Here is the oscilloscope output. Let me just go to the time domain and enable it in a rolling mode. As you can see, it shows us as the waveform is fluctuating and it shows us a square wave. Now why would that be happening? Because the GPIO pin can only output between 3.3 volts and 0 volts. So when the LED is off, it should be 0 volts, and the LED is on, it should be 3.3 volts. But for a PC 13 onboard LED, it is the opposite. When the square wave is 1, when the square wave is equal to 3.3 volts, then the LED is off, and when the square wave is off, it's 0 volts, then the LED on the board gets turned on. Why? Because the LED is pulled up. When it is pulled up, the difference between the voltages becomes 0, and when it is pulled down, the difference between the voltages become 3.3 volts, and hence the LED glows. With this, we have answered the With this, we have verified that the LED is blinking. And why are the LEDs blinking alternatively? If you still have any doubts, you can ask me in the comments. And yeah, here we can enjoy the output. The alternating blinking LEDs on the same pin. Cool, right? I'll see you in the next video. The next video is going to be about pulse width modulation.